One of my colleagues at Input Output bought some Ada for his nephews and nieces. And of course, I don't know any details about that. But just imagine you want to make a gift of Ada to a child. So you want the child to own the Ada, but you only want the child to have access to the Ada when he or she turns 18 or 21 or whatever. And using Plutus, this is very easy to implement a scheme like that, a vesting scheme like that. So I copied the isData contract and into a new module that I called vesting. And as our first example of a validator that actually uses the context, I want to try to implement this vesting idea. So you put money into a script and only the dedicated person can retrieve it, but only once a certain deadline has been reached. So the first step is to think about the types of datum and redeemer. And datum, I think in this case it makes sense to have exactly these two pieces of information, the beneficiary and the deadline. So let's define this type. Let's call it vesting datum. Let's make it a record type with those two fields, beneficiary of type, well, how do we identify the beneficiary? By his or her public key, or to be more precise, public key hash. And then we need the deadline. That will be of type POSIX time. We can derive a show instance. Might be useful for debugging. We don't need the mySillyRedeemer anymore, but we do need an isData instance of our vesting datum. Right, so the first argument is the datum, so that's now of type vesting datum. So for redeemer, do we need any information in the redeemer? What do we need in order to check whether a transaction is allowed to spend this script output? We need to know that it has been signed by the beneficiary, and we must know that it's only submitted after the deadline. But those two pieces of information are both contained in the transaction itself. So we don't need anything in addition to that in the redeemer. So we can just use unit for the redeemer. So first argument, now we need it. So let's call it dat for datum. So the redeemer is just unit. And now we can't any longer ignore the context. So let's give it a name. Right, so now we need to check two conditions: that the transaction is signed by the beneficiary and that it has been submitted, or that the current time is after the deadline. So let's delegate it into helper functions, and let's just write the general structure. So let's say beneficiary's signature missing. So this is the error message we get in case it's false. And let's call that something like signed by beneficiary. And so we need the second condition, that the deadline has been reached. So deadline not reached. Let's call that deadline reached. Okay, and of course these two, signed by beneficiary and deadline reached, we must define. And for both we will need this txinfo. So let's first define that, type txinfo. And that I am here in the REPL and I imported ledger and asked for the information on the script context again. So in order to get the TX info from the script context, we must use this field name script context TX info. So that's script context TX info of our context. Now we can define the two conditions. Let's first do the signed by beneficiary. That's of type bool. Okay, how do we check that? Well, if we check in the REPL again, there is a function called tx signed by that takes an tx info, which we now have, and a pub key hash, and then says whether that transaction that tx info refers to has been signed by this public key hash. So we can use that. So tx signed by info, which we just defined, and now we need the public key hash of the beneficiary, and that we have because we have the datum dat, and this is of type vesting datum, and we have the beneficiary there. So I can do beneficiary of dat. So that's our first condition. And the second condition, deadline reached, also of type bool. So how do we check that? So if we look at this crude diagram, so this is time, and let's say the deadline is here, and let's consider a transaction with, let's first say this validity interval. So recall what that means. Before the validator script is run, other checks are made, including the time check. So the node checks whether the current time falls into the valid range of the transaction. And only then is the validator run. So we know now that we are in the validator, the current time lies somewhere in the validity interval. But if this here, the first one, would be the validity interval, then the current time could be, for example, here, which would be fine. It would be after the deadline. But it could also be here, which would not be fine. It would be before the deadline. So this validity interval is no good for us. We mustn't declare the transaction to be valid if this is the validity interval. This, on the other hand, is fine. We still don't know where the current time exactly is. It can be anywhere in this interval, but no matter where it is, it's after the deadline. So we must check that we have this situation, that the whole interval is to the right of the deadline. And one way to do this is to use this contains function that we played with earlier, and look at this interval, the half open interval that starts at the deadline and stretches into infinity. And if this interval contains the validity interval of the transaction, then we are good. Then we know no matter where the current time is, it will be after the deadline. So we can use contains. Now the interval starting at the deadline is from, and the deadline we can get from the datum. And now we need the validity interval of the transaction. And that, if we look here at the information of the TX info, then this was called TX info valid range of the info. And that should be it. Next, let's look at this dummy type that wraps up datum and redeemer type. Typed is now not a good name. Let's call it vesting. And the datum type is now our vesting datum type. And the of vesting, the redeemer type is just unit. Okay. This is just boilerplate. We must just put the right types here. So vesting datum and unit. This should go fine. Now, of course, we also have to change the off-chain part. But as before, because the focus of this lecture is on on-chain validation, I already prepared that and we'll just briefly go through it. And I should also mention that at the top of the module, I added some additional GHT extensions like derive any class and derive generic, and also added some imports like to JSON, from JSON, generic, and so on. So let's briefly look at the off-chain part. So this type here, vesting schema, defines the endpoints that we want to expose to the user. And as before in our silly example from last week, call them give and grab. So give is for the person that wants to set up this vesting contract, and then grab for the beneficiary to collect. So what parameters do we need? For give, what this endpoint will do is it will create a UTXO at the vesting address with the specified amount and the correct datum. And if you recall, our vesting datum contains the beneficiary and the deadline. So this give endpoint must in particular know those, the beneficiary and the deadline. So this is here. And we also, of course, have to specify how much money we want to put at this UTXO. Therefore, I need a third field, the amount. The grab endpoint, on the other hand, doesn't need any parameters because the beneficiary will just look for UTXOs sitting at the vesting address and then can check whether he is the beneficiary and whether the deadline has already passed, and can then pick those UTXOs and consume them. And we know from the way that we wrote the validator that that will then succeed and no additional information has to be supplied. Let's briefly look at the endpoints. First at give. So it takes the give parameters. And first I compute the datum I want to use. So recall I need the beneficiary and the deadline, and I can get those simply from reading it from the give parameters. Now for the transaction, I need as constraint that I want to create a transaction that has an output at the script address. So I use this must pay to the script with the datum I just defined, and then I must provide the value. So I take the value, the amount from the give parameters, and then use this function here to convert that to a value in Loveless. The rest is as before. I just changed the log message. So I mentioned the amount, the beneficiary, and the deadline. Now for the grab, that's a bit more involved because there can be many UTXOs at this vesting address, and some of them might not be suitable for me, either because I am not the beneficiary or because the deadline has not yet passed. So I grab the current time, I look up my own public key and compute its hash. And then I look at all UTXOs sitting at the script address, but I filter those. And the filter is defined here. So I get such a UTXO, and then I first check the datum hash, whether so I first check the datum hash, and if I find it, it's this age, then I try to look up the corresponding datum. And recall what I said several times before, the producing transaction, so in our case the one that has been produced by the give endpoint, doesn't necessarily have to contain the datum. It can only contain the datum hash. But if that was the case, then I would have a problem here in grab. I wouldn't be able to find the datum that corresponds to a UTXO that I find. But by using this must pay to the script constraint, I make use of the option to include the datum into the transaction. So this transaction will actually optionally contain the datum. So it will contain the datum. And that's why I should be able to find it here, look it up here. So I have this datum, and then I must deserialize it. So this is of the data type, but I want a vesting datum type. So that's the last step. So if all of this succeeds, then I can check whether the beneficiary of the datum is myself and whether the deadline doesn't lie in the future. So at this point, the UTXOs are only UTXOs sitting at this vesting address where I am the beneficiary and where the deadline has been reached. And if I find no such UTXOs I just log a message that nothing is available and don't do anything else. And if there's at least one, then I construct one transaction that consumes all of them as inputs and pays the money in there to my own wallet. So I have to, as lookups, provide these UTXOs, and I also have to provide the validator script. Recall, if a transaction wants to spend the UTXO sitting at the script address, the script must be provided by this spending transaction. So this lookup here takes care of that. And this here, I basically just go over the list of all UTXOs and say I want to spend that one. And as I said, by default, the time range of a transaction will be this always, the time range that starts at Genesis and goes on forever. So if I don't do anything, I would use that, and that wouldn't be good because then validation would fail, because recall, validation checks that the deadline has passed and it only knows that the current time lies in this validity interval. So if the validity interval is from the beginning of time to the end of time, I have no information, and then I wouldn't be able to be sure that the deadline has passed. So I must provide a different validity interval, and that I can do with this must validate in constraint. And here I pick from now. It's just important that everything in the interval that I provide here is after the deadline. But so I could, for example, just use the singleton interval now. But then I would have a problem if the transaction doesn't get there in the same slot to the node for validation. So if it only reaches their slot later, then the current time at that point would already not be in this interval anymore, which only contains now. So the best is to make it as large as possible. So I start at now, but then let it last into eternity. And the rest is same as before. And then I just bundle them up in this endpoints contract and some boilerplate for the playground. Let's try it in the playground. So we see that the playground has changed. Earlier last week we saw that the default amount was 10 Loveless, which is too low because fees are now included, and the fees are normally higher than 10 Loveless. So this default was no longer adequate. So now it's, what is it? 100 ADA is the default value. So let's add a third wallet. And I want wallet 1 to make gifts to wallet 2 and wallet 3. Okay, so wallet 1 starts, makes a gift. And normally it would be possible to submit all 3 gift transactions in the same slot. So I wouldn't need await action. But the way I implemented it, the gift endpoint, after submitting the transaction, I wait for confirmation. Maybe I shouldn't have done that, but it is what it is. And that means before this gift endpoint returns, the transaction must be confirmed. So we do have to wait. So let's wait one block. And a second GIF. Let's wait another block. And the third GIF. Oh, I pushed it once too often. Okay. So the idea is wallet 1 makes 2 gifts to wallet 2 with different deadlines and 1 gift to wallet 3. So now we have our first problem. What is the public key hash of wallet 2 and of wallet 3? There is a way to find out what it is. So let's switch to the REPL. Let's load our module. Let's import ledger. And let's import wallet.emulator. Now, first of all, we have a wallet type, and we see wallet is just a new type wraparound integer. Secondly, we have something called wallet pubkey. Given a wallet gives us a pubkey. And finally, we have pubkey hash, which given a pubkey gives us the pubkey hash. So putting all of these together, we can do pub key hash of wallet pub key of wallet 2, and there we have the hash, and wallet 3. So let's grab the pub key hash of wallet 2 and let's put it in the first two gifts. Let's grab the pub key hash of wallet 3 and put it in the third gift. Next problem is the deadline. In last lecture, I showed you how to convert between slots and deadlines, or POSIX times, but unfortunately this has changed in the meantime. So back then you just needed a slot and out came a POSIX time. Now there's a second argument. If we go back to the REPL and import ledger times slot, then there's a function slot to begin POSIX time. And this now takes a slot config and a slot to give us a POSIX time. By the way, there are versions with begin and end. This is because a slot is not just a point in time, it's a duration in time. So it has a beginning and an end. So these two are for that. So what's this slot config? That contains the slot length and the 0 slot time, so that POSIX time at which slot 0 starts. So now we have to find out what slot config to use for the playground. Luckily, it's the default slot config. So what's the default slot config? For that, we need to import yet another module, data.default, and that defines a class called default, lots of instances. And we see it has a def method of type A. So if a type A is an instance of class default, then by using def we get an A. So the idea is that that is then the default value. And if we check slot config again, then now that we imported data.default, we see it is indeed an instance of default. So by using def and telling the compiler what type we are interested in, we get the default slot config. So we see slot length 1000. So that means POSIX time is obviously in milliseconds. So the 1000 is 1 second. And we see when in the playground slot 0 starts. So now we can use the slot to begin POSIX time and can use def as our slot config. And now we can, for example, see what POSIX time slot 10 begins and slot 20. So let's take the POSIX time for slot 10. And let's say the first gift to wallet 2 has a deadline of 10, and the gift to wallet 3 has a deadline of 10. And let's take the POSIX time for 20. Say the second gift to wallet 2 has deadline 20. Now let's add amounts, let's say 10 ADA each. Okay, and now let's first check the scenario where everything works perfectly. So let's say wallet 3 grabs at slot 10 when the deadline for wallet 3 has passed. We don't need any parameters or arguments for grab. And let's say that, let's wait until, not wait for, and here as well, wait until slot 20. And now wallet 2 grabs. So both gifts for wallet 2 at that point should be available. And finally, we wait one more block for giving it a chance to process and end up on the blockchain and evaluate. Okay, let's look at the transactions. So as always, slot 0, first one is the Genesis transaction that distributes the initial funds. So wallet 2, 1, 3 all get 100 ADA. Slot 1 is the gift from wallet 1 to wallet 2 with deadline 10. So we see almost 90 header change go back to wallet 1, and 10 are locked by the script address. So the second one is the gift to wallet 2 with deadline 20. So now the change is 80. So wallet 1 has 80 left. Another 10 go into a different UTXO in the script at that script address. Finally, the third gift. Now wallet 1 ends up with 70, and another 10 go into a third UTXO at the same address. Now in slot 10, this is now where 3 grabs, and that succeeds. So the third UTXO is the input, is spent, some fees are paid, and wallet 3 ends up with roughly 10 ADA. Finally, slot 20, wallet 2 picks up the 2 UTXOs that were for wallet 2. Both deadlines have passed at 10 and 20. Some fee is paid roughly twice, because now 2 validators have to run for each script input. And wallet 2 ends up with roughly 20 ADA. And the final balances should reflect that wallet 1 has 70 left, wallet 2 has roughly 120, and wallet 1 has roughly 110. So that all works as expected. Let's try what happens if wallet 2 doesn't grab at slot 20 but only at slot 15. Okay, so the first transaction should be the same, and now the transaction at slot 15, only one input, because the second UTXO, the one with deadline 20, is not yet available. So only one input, and wallet 2 only ends up with 10. And we see that still 10 are still locked at the script address. So those can only be claimed by wallet 2 after slot 20. There's one thing I should point out, that I wrote the off-chain code, the wallet code, in a way that only submits the transaction if it can actually grab the UTXO. If you recall, I filtered the UTXO to check that I am the beneficiary and the deadline has passed, which means that we don't really exercise the validator, because we only send transactions to the blockchain that then get validated, that will pass validation. That's how we wrote the wallet code. So if you want to actually test the validator, you would have to modify the wallet code. If you like, you can do that as an optional homework. So remove these checks in the wallet and just try to grab everything. And then it should fail if you are not the beneficiary, or if the deadline has not yet been reached. And then it should fail during validation, not already just in the wallet, not even submitting the transaction. So you always have to be careful, or keep that in mind. Everybody, of course, can write off-chain code. So even though now it works, as long as you use the grab endpoint that I provided, I mean, I wrote it in a way that you never try to claim something that's not for you. But of course, somebody else could write a different piece of off-chain code that doesn't try that. And then if your validator is not correct, if it, for example, forgets to check the beneficiary or the deadline, then something could go horribly wrong. So you must keep that in mind, that only because it works for the endpoints you have provided doesn't mean that somebody else couldn't come up with other endpoints where it doesn't work. Okay, so this is the vesting example, where we made use of the context for the first time, and where we made use of this valid time interval in the transaction to implement a deadline.